Here we have a quick checkpoint to let you have a warm up for your brain. So here it says the figure. This figure shows two protons, symbol P. Okay, so this one and this one are protons, and then one electron on the left side. Of course, practically a proton should be much larger than an electron, but here just show three particles with similar size, just for demonstration. Okay, so here it says on the central proton, what is the direction of the force due to the electron? Okay, so what is the force acting on this proton due to the electron on the left side? Okay, so which direction? Okay. 有没有想法？上下左右啊？应该不会上下吧？那就左还是右？左还是右 ？Acting on this proton. Left. Left. Yeah. Yes, of course. Yeah. Because this electron is a negative. Charge particle. This proton is positive charge, so they will attract each other. So the force acting on the proton is actually pointing to the left side, and of course there should also be a force acting on the electron pointing to the right side. Although the question does not ask you to answer this point. Okay, so for the question B, the force due to the other proton, the force due to, of course, it's still asking you the direction of the force acting on the central proton, and then it asks you the force due to the other proton. Okay, so left or right? Still left. Yeah, because this is still positive, so two positive protons will repel each other. So the force, maybe I call this F12, and then this is F23. They will repel each other. So this is also left. And then for C, the net force. Okay, so this one, these two forces are all pointing to the left side. So the total force should also be pointing to the left side. So this is just a very easy checkpoint to let you have a slightly warm up. Okay, so here we have a sample problem, 21.01. Okay, so here it says a figure A shows two positively charged particles fixed in place on an x-axis. Okay, so this is the x-axis, and usually we have a positive on the right side, and then the charges are Q1. This one is Q1, and then which is 1.6 times 10 to negative 19 coulombs. And then Q2 is this one, is 3.2 times 10 to negative 19, should also be Coulomb. And the particle separation is R equals 0.02 meter. 0.02 meter. Okay, so this is the separation. Okay, actually the distance between these two charged particles. So what are the magnitude and direction of the electrostatic force on particle 1 from particle 2? Okay, so ask you the force acting on this one. Okay, so it is really simple. So it is nothing but F12 equals K, or maybe I can write it as a 1 over 4 pi epsilon naught. But actually you can just call it K, but yeah, actually it's the very first example. I just write the whole term. Okay, so actually when you need to determine the direction, you can actually use the vector form. Okay, so just mentioned last lecture. So you plug in, you need to determine the r-axis, something like this, and then the our head is something like pointing to the left side for the Q1 charge, and then you plug in the correct polarity, whether it is a positive or negative charge, and in this case, both Q1 and Q2 are positive. So you just plug in all the number with a correct polarity, and then you will see all the F should point to the same direction as our head, so you know F12 should be pointing to the left side. Or you can just based on your understanding, okay, this one is positive charge, this one is also positive charge, so they will repel each other. In that case, you can imagine the force acting on Q1 should be pointing to the left side. So you have either way to determine. Okay, so here we can just use the later method. So in this case, we just need to consider the absolute value of the force is okay. So we just take the absolute value, although both Q1 and Q2 are positive. So you don't see why I need to put an absolute value here, but the idea is, I just try to assure that this value is a positive value, and then, okay, so this is the this will be the magnitude of the force, because if you are asked what is the magnitude of a vector, which means it should be a non-negative value. Maybe it can be 0, but it cannot be a negative value. Okay, so will be a positive value with a direction for a vector. Okay, so in this case, 1/4 pi epsilon naught is actually 8.99 times 10 to the 9th power, and then times, okay, here is 1.6 times 10 to minus 19, and then Q2 is 3.2 times 10 to negative 19. And then this should be capital R square. This would here. Okay, so this is 0.02 meter square. Okay, so actually you can just press it in the calculator and then calculate for you. So the answer will be 1.15 times 10 to negative 24 Newton. Okay. So as I mentioned, the SI unit for the answer is important. You don't actually need to put all the unit in between. You only need to make sure you know the SI unit for the answer is already okay. Yeah, because if you need to put all the SI unit here, it will be a burden. So yeah, so make sure for every answer in your quiz or exam, you need to have the SI unit for the answer. Okay, so this is the magnitude, and then actually we can just write it as something like this. F12 will be negative 1.15 times 10 to negative 24 Newton, and then we use a vector form to represent this. Okay, so but of course just now I mentioned that the magnitude is actually this one. This is the magnitude. This is the magnitude, and then if you need to answer the direction, it should be pointing to the. You can say it is pointing to the left side, or you can say it is a negative x-axis. Negative x-axis, or you can put it like a negative x-axis would be more correct to answer this question. But here I would just like to also introduce this kind of representation with the unit vector. Okay, so in the Cartesian coordinate 就是这个叫做笛卡尔坐标嘛，笛卡尔坐标，或者是叫做直角坐标系嘛，直角坐标系。Okay, we will use for the x-axis. The unit vector is I hat. Okay, so we don't try to draw that dot, but yes, sometimes I just write the dot there. But in the textbook, you only have the lower part of the I, and then without the dot, and then with this, we'll call it I hat. I head。 OK， 就是有个头啊，那就表示 x 轴的 x axis 的单位坐标啊。那 y 轴 for y axis will be j head j head, and then for z axis will be k head. We will use this kind of vector notation later on, but actually we can do something like that, because if we try to represent a vector with the Cartesian coordinate, it is already like we already decompose it in xyz component, and then we can do the vector addition very quickly. Okay, so this is pretty much for the question A, and then for the question B, it asks you for the figure C here. Okay, is identical to the previous one, except the particle 3 now lies on the x-axis between particle 1 and particle 2. Okay, so we put an additional particles here in between, also on the same x-axis. Okay, so particle 3 has a charge Q3. Okay, this time it's a negative charge, negative 3.2 times 10 to negative 19, also Coulomb. Okay, and it is at a distance 3r/4 from particle 1. Okay, so this is the distance. Okay, what is the net electrostatic force on particle 1 due to particle 2 and 3? Okay, still asking you the force acting on Q1. Okay, but here we have two additional charge on the right side, so there will be two force acting on Q1. So, but Q1 and Q2, the relative distance doesn't change, so F12 should remains. So we don't need to compute it again. So what we need to calculate is only F13. F13 will be K times Q1, absolute value of Q1 times absolute value of Q3 over the distance between Q1 and Q3, which is 3/4 of R. So 3/4 times R, and then whole square. Okay, so then we only need to plug in the value. K is 8.99 times 10 to the 9th power, and then times Q1 is still 1.6 times 10 to the negative 19, and then the absolute of Q3 is 3.2 times 10 to negative 19. Okay, although it is a negative charge, okay, but actually we take an absolute value here. We only care about the magnitude. So here we only have a positive value, and then here 3/4, and then times 0.02, and then whole square. Okay, so using the calculator, you can also get it is 2.05 times 10 to negative 24 Newton. Okay, so this is the magnitude. This is the magnitude. But okay, this is actually not the answer yet. This is only one of the two forces acting on Q1. Okay, so the total force acting on Q1, okay, maybe we can try to write it as a F13 vector will be 2.05 times 10 to negative 24 Newton. Okay, this time also lying on the x-axis, so I hat, but here this is positive, this is negative. Okay, so they attract each other. The force due to Q3 acting on Q1 should be pointing to the right side. So this is the positive x-axis. So this time is a positive 2.5 times 10 to negative 34 Newton. I hat. Okay, so in such a way, F1 common net. Okay, so the net force acting on Q1 should be F12 plus F13. Okay, so which means we need to add this force with this one. Okay, so this is nothing but 9 times 10 to negative 25 Newton, and then I hat, okay, positive. So the net force is actually pointing to the right side, okay, or the positive x-axis, positive x-axis. Actually, in the exam or quiz, if you are asked what is the direction, you only need to answer either of these is okay. But I here just to mention that both, in this case, both y and positive x-axis mean the same thing. Okay, so this is pretty much about question B. Okay, so this is still very simple. Okay, so for question C, okay, here is that in figure E, okay, is identical to the previous one except the particle 4 is now included. It has a charge Q4 with the same amount, okay, so see here, okay, is at the distance 3r/4 is still the same, but it is not lying on the x-axis anymore. It is actually lying on a line that makes an angle theta equals 60 degrees with the x-axis. Okay, so actually this is the theta, which is 60 degree, and then the distance is still the same. Okay, so here we have so here Q1 Q2 doesn't move at all, so still we have a F12 to be this value, and then actually F14, the magnitude of F14 should still be equal to F13, okay, because Q1, Q4, the value doesn't change, and then the distance doesn't change either, so the magnitude doesn't change, so it is still 2.05 times 10 to negative 24 Newton, okay, but if we need to write it in the vector form, it is different because we need to decompose it for the x-axis component and y-axis component. Okay, so the vector form will be a little bit different. So it will be something like 2.05 times 10 to negative 24 Newton, and then we have a cosine 60 degree times I hat, and then plus sine of 60 degree j hat, something like this. Okay, so so this one will be this value multiplied by cosine of 60 degree, okay, and then this one will be times sine of 60 degree, okay, sine of this sine divided by this sine is a sine of 60 degree, okay. So it will be something like 1.025 times 10 to negative 24 Newton I hat plus 1.78 times 10 to negative 24 Newton J hat. Okay, so this is the F14. And finally, we need to find the net force acting on particle 1. So which means F1 net here is F12 plus F14. Okay, so finally it will become negative 1.25 times 10 to negative 25 Newton I hat plus 1.78 times 10 to negative 24 Newton J hat. Okay, so this is pretty much the force acting on particle 1. It doesn't ask you the magnitude and direction because it is not actually pointing to along the x-axis or y-axis. It is somehow pointing to this. Okay, so if you really need to answer what is the magnitude or direction of this force, actually you need to, let's say, if you need to find the magnitude, it would be something like take the square root of negative 1.25 25 times 10 to negative 25, and then square plus, and then 1.78 times 10 to negative 25 square, something like this. This will be the magnitude of this force. Although this question doesn't ask you, but I just let you know something like this. And actually, this is nothing but the Pythagorean theorem， 就是那个毕氏定理或者叫勾股定理啊。And if you need to find answer what is the direction, and then you need to find the angle. You need to actually find the angle here, okay? Or maybe you need to find the angle here, okay? By taking the arctangent, taking the arctangent like, okay? So you know this one, and then divide by this one. This one, let me call it A, this one we call it B. So A over B will be tangent of this angle. Maybe I call it phi. Tangent phi will be this one, and then you will take phi to be arctangent of A over B. And then actually you need to answer what is this? What is this? Will be, let's say this is also a phi. Okay, this phi will be 90 degrees plus this phi. Okay, will be the answer. Although I don't have a number on my hand, but if you really need to answer what is the direction, you need to find this angle, and then you will say it is phi. Maybe I'm not sure whether the number maybe around 100 degree. Counterclockwise to the x-axis, maybe like around 100 degree counterclockwise, 逆时钟的方向 counterclockwise to the positive x-axis, to the positive x-axis, something like that will answer the question if you are asked what is the direction of the force. Although in this question you are not asked about that. Okay, so any questions? Okay, it is actually very simple. Okay, so here we have another one. It is actually sample problem 21.02. So here it says figure A shows two particles fixed in place. A particle of charge Q1 is positive AQ. We don't know the value of Q, and actually we don't need to know at the origin. Okay, so this is Q1 with the charge amount of 8Q. So this is this is actually 8Q. Okay, and then a particle of charge Q2 is negative 2Q. Also, this is negative 2Q at x equals L. X equals L. So the distance between them is capital L. So at what point other than infinitely far away can a proton be placed so that it is in equilibrium? Equilibrium means there is no net force acting on that added particle. 就是加进我们要把一个质子要把一个质子加进来要把一个质子加进来，在某个地方让它没有力的作用，没有力作用在它上面。So is that equilibrium stable or unstable? Stable or unstable? Okay. So although this in this problem the sense of stable or unstable is not quite rigorous. It's not quite rigorous. So actually in control theory, the definition of stable will be more complicated. But here you just try to mention that if there is slight force acting on it, maybe if it is stable, it will go back. If it is not stable, it will just go away. So somehow like that. Okay, so here is the argument. We need to determine which part of the x-axis we should put this proton, okay, because we need to put a proton somewhere to make it have no net force acting on it. Okay, so a quick argument is that this proton can't be outside of the x-axis. Okay, you cannot put the proton here, yeah, because there will be force acting either this way or that way, and then for the Q2 either this way or that way. So it has no sense to cancel the y-axis component. So you can never place a proton outside of the x-axis. So which means that we can only put this proton on the x-axis, and here the x-axis is separate into 3 parts. I mean, it is cut by the Q1, Q2 into 3 parts. Okay, the first part is here, and then the second part is in between, and then the third part is actually on the right side. Okay, so we separate, and actually the Q1, Q2 separate the x-axis into 3 parts. So we try to argue which part is possible. Okay, so for the first case, if we try to put this proton on in the region 2, which means in between. So and actually Q1 is positive, Q2 is negative, and then of course a proton, 质子, is also positive. So which means that for Q1 acting on this proton, the force should be pointing to the right side, and then for Q2, this is negative, this is positive. So they attract each other, so the force acting on P on the proton should also pointing to the right side. So both forces are pointing to the right side, so they can never cancel each other out. So for this case, we will try to discard this case. It is not possible to make the proton equilibrium in between. So for the second case, if we try to put this proton on the left side, which means region 1, okay, so here try to repeat the same argument. We will find that for Q1 and proton are positive, so the force acting on this proton is pointing to the left side, and then Q2 is negative, this is positive, so the force acting on the proton is pointing to the right side. So yeah, so one is left, one is right. Whether the force can cancel out, yeah, the answer is still no. If we try to go slightly deeper, we will see that this Q1 is 8. This Q1 is 8Q. Okay, we don't know what is the value of this Q. We don't really need to. And for this Q2 is a negative 2Q, as I mentioned. So which means that considering the absolute value, this Q1 is larger. This Q1 is larger. And then for the distance between them, okay, so for the distance between the Q1 and the proton, the distance is shorter than the distance between Q2 and the proton. Okay, so if you try to slightly look into this, F equals K times QA QB over R squared. Okay, something like this. Okay, so this force is proportional to the charge amount, okay, and then inversely proportional to the square of the distance. Okay, so which means that for HQ, this is larger than negative 2Q, larger than absolute value of negative 2Q. Okay, so this one will provide a larger force, and then for smaller distance, this will also provide a larger force. Okay, for the Q1. So which means that F1 always will always be larger than F2. Okay, so which means that if you slightly go into here without doing any calculation, we just comparing the whether the value is large or small. Okay, we can simply argue that F1 always is larger than F2. Okay, so we also discard this situation. Okay, so the remaining one is here. Okay, so for the region 3, like this. Okay, so here we try to also look into this one here. Okay, so still Q1 is HQ. Okay, Q2 is negative 2Q, okay? So for Q1, the charge amount is larger. But the distance is also longer, okay? So the distance will give a smaller value, but the charge amount will give a larger value. So maybe there is a point somewhere so that they will perfectly balance, okay? So we will assume that this distance, this position should be on the right side, okay? Which means we should consider the position of the proton X. The X should be larger than capital L, okay? Otherwise, it will be out of this assumption, okay? Okay, so here we try to calculate the force F1 and F2. So F1 will be K times Q1. Q1 will be 8Q. And then for the proton, it is QP, okay? We don't need to know what is QP either. And then the distance between Q1 and P is X, as we assume, okay? So this is the force F1. This is actually F1. Okay, so it should be equal to F2. Okay, so this is also K times, okay, so we just need to take the absolute value of a negative 2Q, and then QP here. And then here, the distance between Q2 and the proton should be X minus L, okay? So this is X minus L squared. Okay, so, turning to the blue color. So we can actually cancel the K, cancel QP, cancel Q, okay, cancel most of the stuff. And actually this is a 2, okay, so this can cancel the 8 down to a 4, okay. So it remains a second order algebraic equation. So we can just cross multiply. So we have a 4 times, this one is 4x squared minus 8xl plus 4l squared would be equal to x squared, something like this. Okay, so we can simply cancel the x squared. So we have a 3x squared minus 8, maybe we put it lx, and then plus 4l squared to be 0. Okay, so this is nothing but a quadratic equation. So yeah, of course you can just use the negative b plus or minus square root of b squared minus 4ac over 2a, or you can try to factorize it, okay? But yeah, we don't try to go into detail because it is something like the junior school mathematics. So we directly go to the solution. So x will be 2/3 L or 2L. Okay. For quadratic equation, you should have a two roots. Okay, so this is the first one. This is the second one. But at the very beginning, we assume that x should be larger than L. X should be larger than L, but this one is not. Okay, so we would like to discard this one. The remaining one is only this x equals 2L. Okay, so this is the only possible solution. Okay, so this is the first question. It just asks you where we should place this proton, and then for the second question, it still asks you, is that equilibrium stable or unstable? Okay, so we need to make some argument. Make some argument. Maybe I add a page here. So let me draw the figure again. So here we have Q1 to be 8Q at 0. And then we have a Q2 to be negative 2Q. And then this distance is L. And then x is 2L. Okay, so which means it is it should be okay. So this is 2L. From here to here is 2L. Okay, so this is the proton. This is the QP is the proton. Okay, yeah, something like this. Okay, so if we need to really argue this point, whether this point is stable or unstable. So here, what we do is we try to make this x to be 2L plus a small delta L. Okay, we try to put it a little bit to the right side. Try to put it a little bit to the right side, or maybe you can try to put it a little bit to the left side. It is still okay. So let's see what is the force at this moment if we try to make it a little bit to the right side. If it is perfectly x equals to 2L, as we calculate here, the net force acting on the proton should be a perfect 0. But if we try to put it to a little bit to the right side, okay, whether it is positive or negative. So let's see. So here F net, maybe I just calculate the magnitude. Oh yeah. So F will be something like K times 8HQ and then times QP, and then over this is x to be 2L plus delta L and then whole square. Okay, so this is the force due to Q1 acting on the proton. And then for the second part is actually, yeah, so this is positive, this is positive. So they repel each other. So this is a positive value. And then this is negative, this is positive. So for the second one, it should be a negative value. So here we have a negative K times 2Q, or maybe you can put a plus here and then put the negative sign here. Okay, it is the same, and then QP over. So for this one, we need to have here it should be x minus L. This is x equals to L. Okay, so here x is 2L plus delta L rather than 2L. So here we only have a L plus delta L quantity square. Okay, so here we only need to consider whether this F is positive or negative. So we try to factor it out. So we have something like QP, and then we can also factor a 2 out. Okay, so the remaining stuff is actually 4 over this one is a square, so we can just expand it. We have a 4L square plus 4L delta L plus delta L square, and then minus 1 over L plus 2L delta L plus delta L square, something like this. Okay, and then we can try to do a little bit more things. So this is 2KQP, which is a positive value. We don't need to care about it anymore. So here we just need to make it like 1 over L square plus L delta L plus delta L square over 4. and then minus the same thing. 2L delta L plus delta L square. Okay, so here we need to determine whether this one is larger or whether this one is larger. Okay, of course here we try to assume that this delta L is much smaller than the original L. Okay, so in that case we can actually ignore this square term, yeah, because delta L is already very small. Delta L squared should be much smaller than the other term here. Okay, so here is still L squared. Okay, so we need to compare these two fraction 就比较这两个份数谁比较小嘛，那就是分子都是一，分母不一样嘛，就看谁分母大的话，它整个数就小嘛。Okay, so in that case, L square will be the same thing, and so in that case, 2L delta L should be larger than L times delta L. So this one is larger than this one, which means that this whole fraction is larger. So in that case, we know that this whole expression is a positive value, right? Okay, this is a positive value. So what does it mean? Originally, if this proton is placed at x equals to perfectly 2L, then the force acting on it will be a perfect 0. If we slightly put it to the right side, then there will be a positive force acting on it, which means it will further pushing it to the right side, and then it will go away. Okay, so that's the point here. So which means that if we try to put it to the right side for a little bit, it will go further to the right side. So which means that this is unstable. You can repeat the similar argument if you try to put x to be 2L minus delta L. If you have interest, you can try to practice it at your home. Okay, so to make sure that you really understand the argument. Okay, so for this case, you slightly push it to the left side rather than the right side. And if this force is actually pointing to the left side, the argument is the same. You try to slightly put it to the left side, and then also a force acting on the left side on it. So it will further go to the left side. It will never go back. If it is a stable system, it should something like you try to push it to the right side, and then there are force pushing it back, so that it will go back, something like that. Okay, it may be somehow difficult to imagine. Okay, so maybe I can just draw a so suppose we have a curvature， 就是假设我们有一个曲面，我们有一个球，我们可以把这个球就放在最底端，那这个当然是 stable 嘛，就没有 force acting on it 嘛。那如果你把这个球往右推一点，它就会往右，就是会来回正，就回去嘛。就是你往右的话，它就有一个力把它往左推啊，就来回然后就能量消耗掉，它就会回到原来的位置。那这个就是 stable 的状态啊，就实际能够想象的。那如果现在有一个反的凸面，然后通常小朋友喜欢玩一些很无聊的事情，就是我硬是要把一颗球放在它的上面，然后它就不掉下来那我放在上面然后我就成功了，它就不掉下来所以这个也代表说没有力撞在身上。但是如果风一吹，或者是你手碰一下它一往右，它就有一个力往右推它就会跑掉它就回不去。那这个就是一个 unstable 的状态就是 unstable 的状态就是比较好玩，因为我们需要控制它才能够维持着。就好像比如说你要拿一个笔或者拿一个扫把在你的手上面去维持着它 它竖着的状态，这是一个什么叫做 inverted pendulum 啊，倒蛋摆。对，okay. So yeah, so this is pretty much about this sample problem. Is there any question? 有没有问题啊？有问题的话用中文问有没有问题？有没有想要再说明的？如果害羞的话，可以下课再来问，也可以。如果没有问题的话，我们先继续吧。Okay, so here we talk about the charges quantized, 电荷量子化 Okay, so this is nothing to say, nothing but electric charge is quantized, restrict to certain values, 就是它不是一个连续的值，就如此而已。Okay, so here it says the charge of a particle can be written as n times e, where n is positive or negative integer, and e is the so-called elementary charge. So this is really important constant. So any positive or negative charge q that can be detected can be written as q equals ne, n equals plus or minus 1, 2, 3, so on and so forth. Maybe n equals 0 is also okay if it is neutral. Let's say a neutron is electrically neutral, so it don't have any charge. So n equals 0 is also okay. And here we introduce a value called E. Okay, so this is so-called elementary charge, 叫做基础电荷。So it has the approximate value of E equals 1.602 times 10 to the negative 19 C, but usually 1.6 times 10 to minus 19 is already sufficient. So usually in the quiz or exam, you use 1.6 times 10 to minus 19 is okay. We don't need 4 significant digits. Okay, so here is a table. Just mention that in high school chemistry, if you try to break an atom, so it will be 3 types of particle. One is called proton, one is called neutron, and then one is called electron. Okay, so for the proton, it has a positive E, and then for electron, it has a negative E, and then for the neutron, it is electrically neutral. So nothing but that. And then here is also mentioned that when a physical quantity such as charge can have only discrete value rather than any value, we say that the quantity is quantized. 就是这个叫做量子化，就只能够数一些离散的数字，它不是一个连续的数。So it is possible, for example, to find particle that has no charge at all, or a charge of positive 10e or negative 6e, but not a particle with a charge of say 3.57e， 就是小数不可以，它一定是要 1.6 乘以10的负19次方的整数倍。所以为什么它在这里出个题目的话，它也要满足这个物理的这个物理世界的这个量子化，所以它不能够随意乱出一个数字在这里。Okay, so here we also have a quick checkpoint. So it says initially sphere A has a charge of negative 50e, sphere A, and then sphere B has a charge of positive 20e. The spheres are made of conducting material and are identical in size. 这个一样大小，一样形状很重要。Okay, so if the spheres then touch, what is the resulting charge on a sphere? On sphere A. Okay, 所以这个一开始的状态是我们有一个 A 球，有一个 B 球。 那这个有正10个，不是，负50，负51，这个有正的21。Okay, so initially it is something like this, and then you try to let sphere A and sphere B touch each other, and then after touching each other, you can also separate it. So, and in that case, you assume that no any charge going in this system or going out from this system. So it asks you after touching, what is the resulting charge on sphere A? Okay. So actually the answer will be the average of these two. So it will be negative 50e plus 20e, and then all over 2. So it will be negative 30 over 2, which will be negative 15e. Okay, so the final situation will be like we have sphere A and sphere B. Okay, we have a negative 15e here, and then negative 15e also on sphere B. Okay, so that's why I mentioned this is identical in size is important, is that it tells you that after touching, these two spheres should share the same charge amount, should share the same charge amount. 就是它们同样大小的话，它就会在触碰完之后，它们各自就会占有同样的电荷量。Okay, so after touching, touching. 然后它们的总电荷量就不会变，因为总电荷量一开始的时候负50加20的话负30，这里负15负15还是30。Okay, so this is a quick checkpoint to let you know something about the charge sharing. Okay, charge sharing for the conductor. Okay, for the conductor. Yeah, for conductor is important. Okay, otherwise there is no free electron. Okay, so here we have another sample problem. Okay, so here it says the nucleus in an iron atom has a radius of about 4 times 10 to negative 15 meter and contains 26 protons. What is the magnitude of the repulsive electrostatic force between two of the protons that are separated by this distance? Okay, 就是说现在有一个铁的原子，然后按照你高中化学的这个理解，这个原子核的话有一个半径 R， 这个 R 是这个值是这个值。然后他告诉你中间有26个质子，中子的话我们就先不管。然后他就问你，如果其中2颗质子的距离是刚好是这样的话，它们的 repulsive electrostatic force 是多大 ？OK， 所以这个题目很简单。So actually this value should be nothing but F equals K times E square, E times E square over R square, nothing but that. So we can just plug in the value 8.99 times 10 to the 9th power, and then times 1.6 times 10 to minus 19 quantity square, and then over this one 4 times 10 to negative 15 quantity square. Okay, so you press the calculator, you will find that the repulsive force is 14 Newton. Okay, so this is the force repelling two of the proton with this distance. 所以你可能会觉得说，为什么这里突然出一个这么简单的问题呢？那这个问题不是叫你怎么算数学，它是用这个题目来告诉你一些物理的。Okay, so here for the question B, it asks you what is the magnitude of the gravitational force between those same two protons. Okay, 他现在问你，他们2个的引力，万有引力是什么啊？ Okay, so for the gravitational force, we can calculate also using this F equals G times m1 m2 over r squared. Okay, so of course you are civil engineering students, so you should be familiar with this kind of mechanics problem. So G is 6.67 times 10 to negative 11. So this is the gravitational constant. And then for the mass of the proton, it should be 1.67 times 10 to negative 27 kilogram. And then the R is the same. R is 4 times 10 to negative 15 meter quantity square. Okay, something like this. Wow. Okay, so pressing the calculator, you will know that this is actually 1.2 times 10 to negative 35. Okay, then that's it. 就是从这个题目来说，就是单纯带一下这两个数字就结束了。那他要说什么故事呢？So actually there are in the universe there are four types of forces. So the first one is the electromagnetic force. Electromagnetic force 叫做电磁力magnetic force 四种力嘛。那第二种叫做重力嘛 gravitational force 我就不拼全个，就重力一个叫电磁力，电磁力，一个是重力，一个叫做 weak force 一个叫做 strong force。那高中物理的话，甚至到这个学期的物理的话，就大家的话，通常就会学前面两个，后面两个的话是一些很硬核物理的东西一个叫 strong force， 一个叫 weak force。weak force 的话，其实是跟那个叫做核反应有关的，就是什么铀元素什么就是那种用核能发电的那种，就是什么核裂变那种，就是它是会有 weak force 它就对，那另外的话还有一些叫做 strong force strong force 的话是描述一些粒子里面的一些很强力的 force 为什么会有那个的话，就是说现在的话就是你知道怎么算 electrostatic force 现在的话当然以一个原子核里面它有一些质子的话，它当然会有这个电磁力。那这个静电力就是电磁力的一种嘛。那电磁力算出来14个 Newton， 它是 repelling 的，两个都是正电荷嘛 ，repelling 它是排斥的力让这两个分开的14 Newton。那它有没有什么吸引它们在一起的？你能够想象到会吸引的力的话，就是重力嘛。重力的话就是吸引的嘛。那这个力很小1.2乘以10的负351.2乘以10的负35。那你从一个力的角度来看的话，这个排斥力这么大，这个吸引力这么小，那它是不是应该炸开才对？所以这里就告诉你说，其实这个原子核要维持着这个原子核要维持着一个稳定的状态的话，其实它要有一些额外的东西让它们维持在一起它不能够说就是单纯靠电磁力重力它们就能够维持着而且你可以简单看得到说，就是电磁力比重力的话会强得多一般来说都是这样的。 电磁力的话其实也蛮常见的。其实比如说你坐在椅子上的话，其实就是靠电磁力因为其实你跟椅子之间是有一个很短的距离，你被那个电磁力所撑着的，但你不一定会感觉得到，但是其实那个是一个叫做电磁力，你不是被电到了，但是它就是一个电磁力。而实际上的话，你就是比如说你坐着，就是跟椅子有一个很小的距离。而实际上的话，这里要告诉一个故事，就是说，高中物理的话，或者是高中化学的话，就告诉你说，一个 atom 一个 atom 它可以分成 proton neutron 还有 electron。就是物理学家在构想这个事情的话，就是说，我们把物质把它拆分，那拆分到一定程度之后，我们就有了元素周期表，就是那个 periodic table 嘛，就是元素，氢氦锂铍硼什么一排到100多，那拆完之后，每个元素它都有一个核。那核的话，我们把它拆开的话，我们有质子、中子、电子。那质子、中子、电子能不能再拆开？Can a proton, neutron, or electron can further be separate? The answer is yes, yes and no. Yes, yes and no. The proton and neutron can be separate, but an electron is not. Is not. OK. 那你可能就会问了，这 proton 跟 neutron 再拆成什么呢？这里有一个叫做 standard model of elementary particle， 就是中文叫做粒子的标准模型标准模型。哇，你就会看到有很多古怪的东西那紫色的我们叫做 quarks 叫做夸克。那绿色的六个我们叫做氢子就是很轻嘛。那右手边红色的叫做boson 叫做 boson 玻色子还有一个叫做 Higgs boson， 就是前几年拿诺贝尔奖那个，就是那个叫上帝粒子那个那我们就不讲到右面那么多。那简单来说，一个 proton 的话，它可以分成2个 up 加1个 down， 但你不需要记这个不会考只是告诉你一些物理故事而已。然后一个 neutron 的话，可以分成1个 up 加2个 down， 为什么？你可以用这个去验证一下你可以看到这里这个 up 的话 ，charge 是charge 是2/3，然后自旋的话是1/2，不需要管它，所以如果你用2倍的 up 的 charge 加1倍的 down 的 charge 的话，它就会是2乘以2/3加上负的1/3，它就是正1这是 proton， 那如果1乘以2/3加上2倍的负1/3的话，它就是0，它就是 neutron， 但它还有质量，但是它不是用 kg 它用了一个叫做mev 除以 c 平方mev 除以 c 平方是什么它其实还是一个质量因为你正常一个小学生都会知道一个公式叫做 E 等于 mc 平方虽然你不知道怎么用，但是小学生应该都会知道这个 E 等于 mc 平方所以其实这个 E 就是一个能量E 就是一个能量，所以这个 2.2 MeV 其实是一个能量，那除以光速的平方的话，就会变成一个质量变成一个质量，大概是这样。OK， 所以为什么中学没有学这个东西啊？那它怎么来的？那其实我们要看哦，它能不能够拆分成更小的东西，要什么方法呢？就是我们希望就把它们加速，然后让它们碰撞。那如果它们碰撞的话，就有机会去炸出一些更小的元件出来。那物理学家的话，就是希望哦，我们找到比如说你要拼乐高积木的那个最基本的那一块积木出来，所以就有一些叫做 quark 的东西quark 的东西。那它有所谓的什么第一代 first generation、second generation、third generation。那越往右的话，就是要越高的能量才能够碰撞出来的，所以有 up down 什么 charm、strange、top、bottom。那有没有第4代我们不知道，可能要更高的能量才能撞出来，因为你看哦，这个是2.2 mega， 这边已经跳到 1.2 的 giga， 然后这个跳到100多 giga。那如果再有第4代的话，那可能就要 Terra 了，但是目前的话还没找到，就是那氢子的话，你就会很快就找到这个是电子啊。所以在这个基本模型里面 ，electron 就是一个基本粒子，你就不能再拆它它就是负1的电荷，但也有一些负1、000的电荷，它们也是氢子。对，然后还没说这个原子核它们为什么维持在一起呢？它有一个叫做 gluon 的东西，这 gluon 呢，中文叫什么？叫做胶子就像那个胶水那样把那些质子它们把它弄在一起把它们弄在一起。那其实那些就是所谓的 strong force， 就是强作用力，因为他们就是说质子跟质子它们距离非常小你又让它维持在一起，那这个力是非常非常的强的比起那个核反应的那种力还要来得强所以这个叫做胶子当然其他的我就不说了，光子可能你也知道那其他的我也不知道是什么。对，那是讲一个物理的故事了，利用这2个很简单的题目是去讲一下这个物理故事而已。Okay, so finally in this chapter we will talk about the charges conserved. So so charges conserved 就是电荷守恒。So it says the net electrical charge of any isolated system is always conserved， 就是守恒嘛，就是。So here it says 2 charged particles undergo an annihilation process， 就是湮灭的过程。Okay, they have equal and opposite sign of charge. Okay, 所以如果有一个正的电子跟一个负的电子它们碰撞在一起，它们2个电荷就会消失总电荷不变，但是会变出很多的能量出来。这个 gamma 就是一些能量，后面会讲到什么是 gamma。And then, if 2 charged particles appear as a result of a pair production process, they have equal and opposite sign of charge. 就是如果有很强大的能量的话，它也可能会出现很多的正电子跟负电子。就是打雷的时候就会产生很多的正电子反正也不用管它是什么，反正就是电荷守恒，就是电荷的总量就不会变了，在一个封闭的系统里面。Okay, so here we slightly talk about this is called the electromagnetic spectrum， 就是这个叫做电池的频谱就是在工程学里面，我们很常是看频率的，就是工程数学里面可能未来的话，很可能会学一个叫做 Fourier transform。 就是把一个信号看它的频率怎么样啊？它的公式啊，大概是讲的像这样的，但不同领域的课本他们都不太一样的。数学的课本有数学的版本，电机的版本有电机的版本，然后其他工程也有其他的版本啊，通讯的书也有通讯的版本。所以我随便写一个教科书里面的一种版本，它就大概像这样，就是一个积分，就是这样，它就会看到哦，这个 time domain 时域的讯号，它在不同的频率omega 的时候，它会长怎么样？它就从一个时间的讯号变成一个频率域的一个表达，其实它们是一样的。Okay, so here let's slightly take a look at this electromagnetic spectrum. So here we have frequency. 看频率嘛。那反过来的话，我们也会看波长。Okay, so wavelength and frequency are inverse proportional to each other. It is something like C equals F lambda. Okay, so this is the frequency, this is the wavelength, and this is the speed of light. Speed of light will be a universal constant, 3 times 10 to the 8th power meter per second for the speed of light in free space. Okay, so starting from very low frequency, and here is around a megahertz. This is around a megahertz level, and then the FM radio, hundreds of megahertz, and then up to here will be something like the microwave, and then around here we will use it for the communication, like the 3G, 4G, 5G, or maybe Wi-Fi is also here. Wi-Fi, you can see a 2.5 gigahertz, a 5 gigahertz for the Wi-Fi signal, and then for the 3G, 4G, maybe using hundreds of megahertz to up to 2 or 3 gigahertz, or maybe for 5G, it will use up to around 29 gigahertz, 29 gigahertz for the 5G. Okay. Okay, so it is close to the millimeter wave. Okay, if you just take a look at here, 10 to negative third is actually the millimeter. It's actually the millimeter for the electromagnetic wave. And then even higher, we have infrared, and then the visible light is that narrow, and then we have the ultraviolet. Okay, so if we go to higher frequency, it has a shorter wavelength, and then for each of this kind of proton, we will have a larger energy. Okay, so ultraviolet 就是紫外线嘛，所以平常特别是夏天要蹭那个防紫外线的，不是防红外线的。And then we have something like the soft X-ray and then the hard X-ray. Okay, so the X-ray has a even smaller wavelength so that it can go through our flesh. Okay, so that it can see our bone or whatever inside our body. And then even higher, we have something called the gamma ray. Okay, 就是一些宇宙的射线啊，所以就是这个 gamma。就是这个 gamma， 就是一些高能的粒子。Okay, so maybe I think this chapter is really simple. I don't think I will go through this additional example. So let us end this chapter here. Okay, so